All right, guys, welcome to Chapter 19, Section B, and a little tiny bit of Chapter 20, Section B. So this is a beefy lesson, so buckle up and let's get ready. All right, so kind of keeping our connection between electricity and magnetism, it's important to note that all matter contains electrons, which gives them the negative charge, and protons, which gives them the positive charge. And that's what causes things to act similarly to magnets, with the opposites attracting and the same charges repelling. Okay, electric current is the flow of that charge through a material. Okay, so we typically have wires that allows electricity to flow through, and that's known as an electric current. We'll talk more about that in the next slide. Okay, some things resist that flow; those are called insulators, and some things allow that flow. That's called conductors. Same with heat. Okay. Insulators and conductors are used the same way when we talk about heat. Insulators block it, conductors allow heat to transfer easily. Okay, so the metal wires that we talk about a lot are very good conductors. They're coated in like rubber or plastic though, because that's an insulator, so you're able to touch the cable without being shocked. Okay, but an electric current actually produces a magnetic field. So we're going to do some demonstrations like that in class, and we'll do one just like this picture. Basically, if you allow current to flow through a wire like that and hold it up to a compass, it will have an effect on the compass, just like holding a magnet up to a wood. Okay. All right. So back to current. Again, it's the movement of electricity through a complete loop. So let me get this here. When we had the little battery, okay, you had the wire going around it. Battery has the wire has to be touching the battery in order for the current to flow. Okay, so we have these diagrams, which we'll talk more about in a later lesson. We'll learn about the symbols. There has to be a complete loop in order for that current to pass. Now you've got two different types of flow. One is a direct current. That's most things that use batteries. And the current flows in one direction. Okay, and you can see that it goes all the way around like that in a loop. And that was something that Edison was really involved with. Now, alternating current, AC, that's something that Tesla was really involved in. The current changes directions periodically, and it follows a pattern, but it doesn't just go in one direction. Now, the things that we plug in our houses are almost exclusively on AC current. Okay, and then current is measured in something called amperes or amps. Okay. And I know there's a bunch of letters here. The A is for amps, but like in italics, I is the abbreviation used for current. So we're going to put a bunch of these things together in a formula coming up. Okay, so I'll show you that again. The next piece of that formula is voltage. So the current has to come from somewhere. The electricity that we talk about has to come from somewhere. And so there needs to be a potential for the charges to flow. So electric potential is that potential for them to flow. And there's a potential because there's a potential difference between the charges. The stronger the charges are, the distance between them has an effect on how much potential there will be for the current to flow. That is measured in volts. Okay, so it's often referred to as voltage. So you can kind of think of it the same as gravitational potential energy. The higher you lift a ball up away from the surface, the more potential energy it has, and the more kinetic energy it will get when it drops. If you can increase the electric potential, the potential difference between charges, same thing. It's just going to increase that flow. Okay, that current. Voltage is another name for potential difference. So this is the same as that, and it's really more commonly used. Okay, that is what causes currents to flow through a complete circuit, and it's measured with something called a voltmeter. All right, voltage sources are batteries. Not exclusively, but that's the easiest way to talk about it. It's the most common source. Okay, this is what creates that potential difference in a circuit. Okay. Generators do this, plug in stuff with electricity also, but batteries are kind of the easiest ones to talk about. So there's different size batteries, which is going to be like the different amount of lift for that potential difference. Okay. And the way a battery works is there's chemicals in a battery, and there's chemical potential to have a reaction. Okay. So the size of the battery determines, the chemical reaction that's going on, and that will determine that potential difference or that voltage for that battery. Okay. The third thing that we're going to talk about for this equation coming up is resistance. Resistance is basically what it sounds like. It's the resistance to flow. Okay, so the current might meet some resistance for some reason. It's an opposition to that, and it's measured in, that's a Greek letter that's called ohms. Okay. The higher the resistance, the lower the current. Okay, even if you have a battery that has a certain amount of voltage, the voltage doesn't need to change. The more resistance there is, the more of a drag there's going to be on the current. Okay, and we'll talk about that more when we get to circuits. So the resistance depends on the wire, basically. That connects the loop for the current. Longer wires have more resistance, and thick wires have more than thin. Okay, so if you think about it as a hose and putting water through a hose, okay, the longer the hose, the harder it's going to be for the water to get through the hose. There's more resistance. Okay, the thinner the hose, also the harder it's going to be for the water to get through. A wide open hose and a short hose, it allows the water to flow the easiest. Same with electricity. Okay, all right. So we're going to put all three of these things together with Ohm's law. So resistance uses the R, and it's measured in ohms. Voltage is measured in volts, and it uses a V. It's the only one that makes sense in these abbreviations. And then current is that capital I. Usually it's in italics, and it's measured in amps. Okay. So we've had formulas like this before. You've got three versions here. It's going to depend on which variable you're looking for. If you're looking for voltage, that means you're going to multiply the other two, the current and the resistance. If you're looking for current, you're going to divide the volts by the resistance. And finally, if you're looking for resistance, you're going to divide the volts by the current. Okay, so let's look at this one real quick right here. Okay, what is the resistance? So we're using this formula right here. What is the resistance of a headlight connected to a 12-volt battery? So that's our voltage with a current of 0.4 amps. So that's the current. Okay, so the volts would go up here. So that would be 12. And the current would go down there at 0.4. And you divide those out and you would get 30 ohms. That's the resistance for that circuit, for that situation. Okay. All right, bringing it back to magnets a little bit. And again, we'll do some demonstrations on this in class. Just remember that an electric current can produce a magnetic field. Okay. And so because of this, you can actually turn a magnet on and off, which is basically the definition of an electromagnet. It's a magnet that can be turned on and off because it's only a magnet when the electricity is flowing through it. So if you turn it on, the electricity flows, magnetic field is created. Turn the electricity off, it's no longer a magnet. Okay, that is the definition of electromagnet. Now, because of this production of a magnetic field and this electrical field, they kind of go back and forth. We use this thing called a solenoid, which is found in motors, it's found in toys, it's found in electromagnets. I'll show you some in class. You guys will get to make some, and you guys will get to play with some. It's basically creating a magnetic field around a cylinder, okay? So if you think of having a nail and wrapping a wire around it like this, okay? This is now a solenoid. If I can put electricity through this wire, it's going to produce a magnetic field on this nail. And I'm not going to do it in this video, but you'll have another video and we'll do this in class, okay? So wrapping the wire in loops causes that magnetic field to collect in the center, okay? Kind of through the middle here, okay? So each loop of this wire is emitting its own magnetic field, and it all kind of collects in the center of that cylinder there, okay? So again, that solenoid is a current carrying wire wrapped in many loops. The current goes into that wire, okay? If you have metal that goes through that, then that metal will be magnetized inside of that solenoid, okay? Nice job. That was a long one. Bye-bye.